Our next speaker is Kazimierz Gofron. Kazimierz received a PhD from the University of Illinois in Chicago on electronic band structure of high TC superconductors. He stayed in the field, did some magnetic X-ray circular dichroism techniques, and moved on then for 5 years into the cellular telecom industry, developing mobile videophone technology. He's now for over 20 years in the synchrotron beamline business at different beamlines across the US. And in his talk, he will present results from the NSLS-II, namely on-axis 3D microscope for X-ray beamlines at NSLS-II.
Thank you for having me. On-axis microscope provides the same view of the target sample as the particle X-ray beam is seeing. The NSLS-II currently operates about 19 beamlines. There are 9 under construction. Endstations contain many microscopes that have a challenge of imaging both beams that are of the order of 1 micron, 4 micron, 4 by 6 microns, and sample or features of 1 micron or even smaller. What I'm particularly interested in is the non-dispersive microscopes to allow imaging not only in a visible spectrum. And then I'll discuss briefly about, or actually quite a bit about computer vision, including the 3D microscope that we've been working on. The concept of on-axis microscope consists of folding the objective away from the particle beam with the aid of a mirror that contains a hole to pass the X-rays through. One of the implementations is on 10ID, where the X-ray beam passes through KB mirror set, and then it is guided to the sample located on top of the Huber stack. This microscope has a working distance of 60 centimeters, 600 millimeters, has a 3x magnification and 3 microns resolution. This is the implementation of that mirror with the hole that allows the X-rays to pass through, and then the visible light coming back from the sample goes with the aid of this mirror, and in our design here is actually folded again with a mirror to allow the cryostat to be mounted on top of the Huber stack. This is the image of the high-pressure cell mounted on this microscope, mounted in this sample location. Another implementation is a higher magnification, which is a dual-view microscope, really the same optics, just higher magnifications, 30x and 5x. At the back of the microscope, there is a beam splitter that allows us dual view, so we can have a large field of view and large magnification with a resolution of about 1 micron, and we've proven it by imaging 1 micron diamond small crystals. Another beamline that is currently under readiness review is a TXM microscope that has 2 optical microscopes in this area and 2 X-ray imaging microscopes in this area. Just to get a guide, there's at least 30 motors in this area to aid with the X-ray optics and also optical axes. These instruments get really compact now. The concept of the X-ray imaging consists of a scintillator which converts the X-ray particle striking a scintillator that emits the visible light, and then conventional imaging is deployed 2x, 10x. The visible light microscope is pretty conventional. It's got also XY positioning stage. This is another type of microscope, which is a X-ray eye, which allows very precise positioning or focusing of the KB mirror set. And here we're doing a VFM focusing of the KB set with the aid of this specific microscope. The microscope is conventional microscope up to this point, where we have a first surface mirror, and then we have a scintillator. I prefer to use cadmium tungstate, high Z scintillators, because the stopping power is very high. The fact that we see two streaks here is because in the first implementation we use the second surface mirror. Don't make that mistake. Use the first surface mirror here. So the resolution, we're seeing the K-beam mirror focusing to about 5 microns in a vertical. That's the second peak is just optical reflection, because when you reverse this prism, actually there's an air gap there, and it's just an image, nothing special. Computer vision, we are using OpenCV with a Python on top, which integrates to EPICS control system, optimizing using Intel primitives, performance primitives, and threading libraries. The pipeline is camera, provides the images through EPICS area detector to the processing, computer vision part, and then we can have the action of moving a motor centering goniostat. This allows automating certain processes, like providing information about image size, characterizing the beam, and then a little bit about 3D microscope. Loop centering, we collect the images as we rotate the sample, we find the crystal location, we plot that, and then we move the motors appropriately. The whole process takes 5 seconds. Characterization of the beam, it's BPM and 10ID, shape, intensity, lots of parameters can be extracted, and then another application where we have a sharp tip typically placed at the goniostat, and we're finding basically a tip of that tip and finding how well the goniostat is centered. This is another use of image processing where we are characterizing the analyzer of the inelastic X-ray scattering beamline. There's 6 crystals back reflecting the beam. They are slightly detuned, so the beams are not overlapping. Normally they would be basically, one would be in the center, the top ones would be shifted down basically. We're detuning so we could separate each energy. And then Python provides a lot of parameters about the beam itself. Application in robotics, we are looking at how the robot grips the sample. And then what is important is this similarity parameter, which you probably cannot see, but this parameter basically is a value from 0 to 1, which actually tells whether the mounting is good or not. And it's basically, this one would be not so good. It's too far from the gripper. And this parameter can be used in terms of whether to proceed with the mount on the goniostat or not. It's a real-time application. Resolution and depth of focus has a fairly known relation. On 10ID, we're working around 3 microns, so our depth of focus is around 20 microns. So if we have taller objects, we only see part of the object in focus. As we move to 1 micron, we've got an even bigger problem, because this depth of focus is well below 10 microns, somewhere in the 5 or 2 or 2 microns, depends on whether the optics is telecentric or not. So how do we get from the image that is focused in one spot to image that is focused globally? So what we are doing is collecting a stack of images. So we're scanning images through the focus and obtaining the regions where the images are focused. Then we're doing alignment. We're using algorithms, and then we're processing it mathematically and arriving at these images. What we are using is OpenCV, Python, OpenGL for plotting, and then this actually works on all 3 platforms as far as we know. We did test Windows, we did test Linux. I have not personally played with Apple. I don't see a reason why it would not work. And wherever possible, we do it in real time. This is actually images obtained on 10ID. Again, this is as they come from the microscope. We didn't adjust the light, so the images were pretty dark. But the key thing is that the only portion of the image is in focus. And again, in another image, the focus is somewhere else. And then what we arrive is the image that is actually globally in focus. This is a depth information, so this is a mask. It gives us information about where the image, which part of the image is at what distance. And that can be used to get the information about the three-dimensional nature of the object that we're imaging. And if you could press the button video, so we're getting some information about the 3D just by doing having that information from the depth. You should ignore this. This is a specular reflection, and the algorithms don't work with these well. We have not adjusted the light properly. It's just our mistake. Thank you. And the next one. Okay, and then again. And this is some mineral that we've imaged. And this is actually conventional 2D microscope, but actually provides some level of a 3D information. And so that was kind of interesting, but we have a crystal harvesting facility where we are collecting biological crystals. And Alexei Soares was kind enough to have his interns collect a set of images for us. And these images were collecting at different distances, different focus. And then we did the image stacking. We obtained the focused image. And what was the challenge there was actually that the technique works only for a while. So they start, so the technique itself is that there's acoustic wave that ejects individual crystal or a group of crystals from like small regions here. And crystals are harvested. It's very difficult to do it manually. It's a lot of work. But what they did notice that initially it works. There's a couple of crystals collected, and then the process stops. So what we did is in the image stacking, we did the three-dimensional profile of this, and we've arrived at the conclusion that actually ejection is only from the surface layer that is only tens of microns. Crystal is ejected, and then the surface layer heals. Typically, the crystals actually settle to the bottom, and basically that was the reason why the technique stopped. The depth map itself looks like modern art, but the key was actually this, that the surface actually heals itself. Thank you.
I actually have one. How do you do the alignment of beam and your objects? And to what precision? You have this different microscopes.
So what we do is actually we place a scintillator crystal, and then at the sample location, and we determine where the beam is striking, beam profile, and then when we place the sample in that location, we have already a crosshair that is provided, for example, by area detector, and then we know exactly where the beam is. But what was really critical about the on-axis microscope is that we've seen, for example, bubbles actually coming out during data collection, and that's something that without having that instrument there, it would be really, it would be very misleading to analyze the data.
Mm-hmm. So radiation damage, you see.
Well, it's heat, radiation, whatever is happening, but we've seen liquid crystals kind of bubbling there, and that was not a good, that's not intended.
At the very, yeah.
Probably I missed it. Did you use some photogrammetry technique in order to get depth images?
No, we've used only that microscope, nothing else. Stacking? Yeah. In terms of distance?
Yeah.
So we actually know, because we are moving the sample, we know how many microns it's moving. So we have the calibration in terms of what the specific position of each image is and where the crystal, for example, is.
okay, but what about the relative distances of the same object?
Relative distances?
Between different points.
I'm not sure I understand this.
I'll ask you offline.
Okay, sounds good.
Thank you, anyway.
Sure.
So let's thank Kazimir again.